So this video is going to be about special right triangles, and so we'll talk about what that means here in a little bit. But I've got a couple of quick questions here. The first one says, or they're both the same. It says, what's the length of the diagonal of each of these squares? And so what I mean by that is this diagonal line, how long is that thing? We'll call it x. And so what we're going to do is we're going to dig back into our geometry knowledge, and we're going to look at this triangle right here. And it's a right triangle since we have a square that's a 90-degree corner. And so we can use the Pythagorean theorem. We're going to do 4 squared plus 4 squared equals x squared. So 4 squared is 16. We've got 16 plus 16 equals x squared. Add that together, we get 32. And then if we want to get x, we're going to square root both sides. And so at this point, you could punch it in your calculator. But what we're going to do today is we're going to make sure we get the exact answer. Excuse me. And so we're going to break this one up. We're going to simplify this square root. And 32 is 16 times 2. And so then this gives us x equals, the square root of 16 is 4. So it would be 4 times the square root of 2. So that diagonal is 4 root 2. All right. So bear with me here. Let's do one more. And then we're going to talk about, see if you see a pattern happening. So we'll call this one x again. This is still a square. And so I'm going to give myself a little bit more room here. We'll do 7 squared plus 7 squared equals x squared. Same idea. 7 squared is 49. And then we add these two together, we get 98. And then when we square root, we're going to break down the square root of 98 into 49 and 2. The square root of 49 is 7, so it would be 7 square root 2. So that means that this diagonal piece is 7 root 2. Well, what do we notice about the 7 root 2 and the 4 root 2? They are whatever the side length is times square root of 2. So that's kind of the pattern that you want to see when you're looking at these special right triangles. And so what these special right triangles are, just so that you understand what I'm talking about, are, in this case, it's a 45, 45, 90 triangle. That's typically what it's called, 45, 45, 90. And where this comes from is you just basically take a square and you cut it in half, and you get a 45, 45, 90 triangle. That's referring to the angles, of course. Okay, so let's say we have some squares, and I already tell you what the diagonal is. Could you figure out the length of each side? Well, we're just kind of working backward then. So if this diagonal is 5 root 2, then that means that each side of the square is, hopefully you're thinking right now, is 5. Because the diagonal is whatever the side length is times root 2. Likewise, with the middle one, if we have 8 root 2 for the diagonal, then that means all these sides are 8. So where this gets a little bit tricky is, what if the diagonal is 3? Not 3 root 2, but just 3. So if you notice, when we're going from, let me see, I'll switch it up. We'll move to white here. If we're going from side length to diagonal, we just multiply by root 2. So if we're going from diagonal to side length, we just divide it by root 2. That's the inverse of multiplying. So let's do the same thing here. If we're going from 3 to the side length, we're going to do 3 divided by root 2. So that's going to be our side length. So once again, we could plug this into a calculator and get some decimal, but we want to do exact answers, and you'll see why here in a moment. But the way we write this is 3 divided by root 2 as a fraction like that. And then one thing you've probably learned throughout your math life is we don't want to leave square roots in the bottom. So we write this as square root of 2 over 2. Excuse me, let me back up a second. The reason I did this is we want to multiply by the bottom to cancel out that square root on the bottom. And so we're really multiplying by 1 here. Root 2 over 2 is just 1. But then when we do square root of 2 times square root of 2, we just get 2 on the bottom. And so since we multiplied by root 2 on the bottom, we have to multiply by root 2 on the top. So this becomes 3 root 2 on top. So each side length on this square is 3 root 2 over 2, 3 root 2 over 2, and so on. Same thing with the top and the bottom. So here's the most special of these 45, 45, 90 triangles is when the diagonal is 1. And so we want to figure out what would these side lengths be if the diagonal is 1. Well, we're going to do 1 divided by square root of 2. And then we're going to rationalize the denominator, we call it. So we're going to multiply by the square root of 2 on top and bottom to cancel out that square root on the bottom. Now, one thing that oftentimes I'll see students do is they will say, well, can't I just square it, square the top and the bottom, so then I end up with 1/2. Well, not exactly. It doesn't really work like that. Let's think of another example. So this is not how you rationalize the denominator. If you're assuming that you can just square the top and the bottom, then you're telling me that 1/2 should, if we square the top and the bottom, that would be the same as 1 squared over 2 squared, which is 4. And 1/2 is not the same as 1/4. Those are completely different fractions. And so squaring the top and bottom is not an okay way to get rid of that square root. That's very tempting, but it's not an okay way to do it. So we've multiplied by 1, which in this case it looks like root 2 over root 2. So the bottom is root 2 times root 2, which is 2 again. And then the top is 1 times root 2, which is root 2. So that means all of these sides are root 2 over 2. So our first very special right triangle is this one right here. We have a 45, 45, 90 degree triangle, and the hypotenuse is 1, and the two side lengths are root 2 over 2. That one is extremely important for you to know, especially once you start getting into the unit circle. So this is one that you'll definitely want to know. All right, let's look at the second case of special right triangles. This one's actually, we started with the harder of the two, so the second one's not quite as bad. So here we have some equilateral triangles. On the first one, all the sides are 6. On the second one, all the sides are 10. And this time it's asking you, what's the height? So the height, we'll just call it x here. So what we're going to do, just like on the last example, is we're going to break this into a triangle, a 90-degree triangle. And so one thing you need to know about equilateral triangles is that all of these angles are 60 in each corner. And so that means that if we have this line, these are both going to be 30. It's bisected. It's cut in half. So what happens when we have this equilateral triangle is we end up with a side down here, whoopsie, of 3. And this side is also 3. It gets cut in half when you draw that height. So let's look at this shaded triangle. I'll draw it down here. We've got a 3 and a 6 and an x. And so just like before, we're going to use the Pythagorean theorem. We're going to do 3 squared plus x squared equals 6 squared. Remember, the c squared is always the hypotenuse, so this one is going to be c here. So 3 squared is 9. 6 squared is 36. We'll subtract 9 from both sides. We get x squared equals 27. And then we square root both sides. And once again, you could type it into your calculator, but we're going to be dealing with exact answers, and you'll see why here in a minute. Square root of 27, I can break into square root of 9, square root of 3. And so this one ends up being 3 root 3. All right, so that's going to be the height of that equilateral triangle. Let's do another example, and let's see if we can find a pattern this time, which we will. Same idea here. We've got 5 and 5 on the bottom. And so if I want to figure out the height of that shaded in triangle, I'm going to do 5 squared plus x squared equals 10 squared. This gives me 25 plus x squared equals 100. We'll subtract 25 from both sides, and we get x squared equals 75. And then when I square root it, I get x equals square root of 75, which is like 8 point something. But what we're going to do is we're going to break this down. So it'd be square root of 25 square root of 3. So then we get 5 square root 3 for the height. All right, so the question is, what's the pattern here? Well, on the first triangle, we had side lengths of 6, and then we ended up with a little side length of 3, and the height was 3 root 3. Here we had side lengths of 10 on that equilateral triangle. And when we cut it in half, we got 5 and 5, and the height was 5 square root 3. So in general, we're going to have, well, we'll talk about this special case as well. So what if all the sides are 1? And I kind of have this one set up here. And we want to figure out the height, x. So what we're going to do is we're going to pull this triangle out. And so we're finding x right here. So instead of doing the Pythagorean theorem like we could do, the pattern I noticed was, if we go back here, is the height, in this case we called it x, we got 5 root 3. And here on the first one, the height was 3 root 3. If you notice, that first number, the number out in front of the square root, is the same as that short side length. And so what we're going to do is, instead of doing Pythagorean theorem, we're going to say this is the short side length 1/2 times the square root of 3. And then typically, so this is right to write it like this. This is totally okay. But typically what you're going to see is you're going to see it written as root 3 over 2. So special right triangle number 2 is just this one that we have right here. So I'm going to clean it up just a little bit, just so you can kind of take some notes. This one is our special right triangle number 2. Is hypotenuse of 1. It's a 30, 60, 90 triangle, we call it. And the short side length is 1. Excuse me, short side length is 1/2. The hypotenuse is 1. The long leg is root 3 over 2. All right, so these are the 2 extremely important special right triangles. And so to summarize, we looked at some special right triangles. We had a 45, 45, 90, a 30, 60, 90, and we saw some rules that came up. With the 45, 45, 90, the 2 sides were the same, and the hypotenuse was that side times root 2. On the 30, 60, 90, the hypotenuse was twice as long as the short side, and the long side is the short one, x, times root 3. The 2 most important ones that you'll ever need to know for any math class are the 2 on the right, when the hypotenuse is 1. Those are really, really important, especially as you start talking about the unit circle and trigonometry. So these are extraordinarily important as you get further along in math. These are ones that you'll need to memorize and know by heart. So that is special right triangles in a nutshell.